So this is chapter 28, quantum physics. So this is the second chapter about what we call modern physics. Now you may chuckle at that. In physics, modern physics means special relativity, which was last chapter, quantum physics, and anything after that. And why is it modern physics? Well, I mean, these were developed late 1800s, early 1900s, so modern, but what's modern about it is that they show that classical physics, kind of like Physics 105, or Newtonian physics, is wrong under certain circumstances. So relativity, what was that all about? Well, it showed that classical physics was wrong when the speeds of objects approach the speed of light. Quantum physics shows that classical physics is wrong when you're trying to describe small things like atoms or things smaller than atoms. Classical physics just doesn't work at all. All right, so here are some objectives. Quantum physics. Understand how X-ray diffraction reveals the atomic structure of matter. Further develop students' understanding of the photon model of light, using it to explain the photoelectric effect. We're going to go in gory detail there, so just prepare yourself. Understand the experimental evidence for the wave nature of matter. Now think about that, the wave nature of matter. We're talking about electrons acting like a wave. That's totally insane, but it's true. Understand how the wave nature of matter leads to quantization of energy. Recognize how the uncertainty principle limits our knowledge of the states of particles. Now, before we start talking about X-ray diffraction, I want to just go over a bunch of quotes I found. And these are just kind of fun. Some of these are quotes from leading physicists, Nobel Prize-winning physicists that actually helped develop quantum mechanics. And that's all I'm going to say. So let's read some. All right. So he's talking about quantum physics, right? He says it, so it's quantum physics. Because quantum physics predicts such a wide variety of phenomena so accurately, quantum theory is probably the most successful scientific theory ever invented. Its practical impact extends to every device or idea that depends on the details of the microscopic world. Electronic devices such as transistors, silicon chips, integrated circuits. And so all the information and communication technologies such as TV, computers, and cell phones, most of modern chemistry and some of biology, lasers, our understanding of different types of matter ranging from superconductors to neutron stars, and nuclear physics, nuclear power, nuclear weapons. Central to the entire high-tech world is an elusive and highly non-Newtonian particle, the electron. Let's keep going. Quantum mechanics, or quantum physics, is the strangest field in all of science. From our everyday perspective of life on Earth, nothing makes sense in quantum theory. All right, so this is Niels Bohr. He was one of the the developers of quantum physics, and he received the Nobel Prize for that. Anyone who has not been shocked by quantum physics has not understood it. Okay, this is Feynman, another Nobel Prize-winning physicist. He came up with his own ways of doing quantum physics. Atoms are completely impossible from the classical or Newtonian point of view. Here's Feynman again. I love this quote. Again, this is Feynman. He came up with his own way of doing quantum mechanics. So, I mean, he knew quantum mechanics, right? Let's see what he says. I think I can safely say that nobody understands quantum mechanics. I am going to tell you what nature behaves like. If you will simply admit that maybe she does behave like this, you'll find her a delightful, entrancing thing. Do not keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you will get down the drain into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that. Okay, this is Murray Gell-Mann. He was another person who did a lot with quantum physics, won a Nobel Prize. All of modern physics is governed by that magnificent and thoroughly confusing discipline called quantum mechanics. It has survived all tests, and there is no reason to believe that there's any flaw in it. We all know how to use it and how to apply it to problems. And so we have learned to live with the fact that nobody can understand it. Regarding quantum mechanics, we must let go of all our preconceptions about the world derived from our experience in our senses, and instead let mathematics lead the way. That's kind of like relativity, right? I mean, time dilation, space contraction, all these crazy things. We don't experience that, but that's because we're not traveling at the speed of light. We don't experience things in quantum mechanics because we're not the size of an atom. So we have no experience to base our thinking on. All right, so there's some things for you to think about. Okay, so let's talk about atoms. X-rays. X-rays. All right, so an X-ray is a form of light, and we can't see it. You recall this narrow band is visible light, and so here are X-rays over there. Okay, so X-rays have a higher energy than visible light. You already know that. I mean, if you go to the dentist office and they're going to take X-rays of your teeth, what do? They put a lead, shield over you, right? Okay, and so as you know, X-rays are used in X-ray machines to take images of bones and things like that. Okay, and X-rays are produced in X-ray tubes, and you saw this slide before. You use conservation of energy to figure out how fast the electron when it hit the target. Okay, so what does this have to do with quantum physics, X-rays? Well, remember when we studied diffraction? So physicists figured out how to use X-rays for X-ray diffraction, and they use it to show that solids have a regular pattern, a repeating structure called a crystal structure. X-ray diffraction was also used to figure out the structure of all sorts of things, DNA molecules, all sorts of things. So it's incredibly important, right? So here's just a quick review of diffraction. We had this not too long ago. So you see that when light goes through a slit, it bends, right? And it forms this pattern, this diffraction pattern. We also saw that when light goes around something like your finger, you see this pattern, this diffraction pattern. We talked about the diffraction grating, remember? A little tiny thing that has maybe 1,000 slits per centimeter or something like that. And a diffraction pattern is produced. And we were able to figure out this equation for the bright lines, we call them bright fringes. D sine theta equals m lambda, where m is that index, right? 0, 1, 2, and all that kind of thing. Okay, so that's all old hat, all right? That's old hat. Well, again, this is a solid, right? This is a solid. You see this crystal structure, right? This regular crystal structure, And people figured out how to use this, similar to a diffraction grating. And, because there's spacing, right? There's this regular spacing between the atoms and so forth and so on. It says there, X-rays are incident on a crystal. And guess what? You can figure out this equation. You'll get the bright fringes, on the screen after the light goes through this at these distances. Okay? So that's kind of cool. You can use a solid, right, as a diffraction grating. But of course, people had to first learn that the crystals had this structure, right? Then once they understood it had this structure, then they used it to do all this information. And so in the real world, you know the wavelength, right? You know the wavelength because, you're setting up the experiment, so you know the wavelength of the X-ray. And you measure, okay, so you know the wavelength. You measure the angles. And so what you're determining, if you know that wavelength and you measure the angles, you're determining the D. And the D is the spacing between these planes of atoms. So this was incredible to help people figure out the structure of crystals and things like that. Okay, so that's that. Now let's talk about the photoelectric effect. And as I warned you before, we're going to go into gory detail. And the reason we're going into so much detail here is because this was probably maybe or maybe one of the most important experiments that forced people to realize that classical physics was wrong on certain things. So we're going to go into detail, right? All right. So here we go. So in other words, this was the first evidence that light acted like particles. Because you remember how we talked about, well, we just did diffraction, right? Diffraction is a wave characteristic. So we spent a lot of time on the wave theory of light, how you do the double slit experiment and you get an interference pattern on the screen. That's a wave characteristic, right? And then the photoelectric effect, as we talked about last time or some time ago, shows that light sometimes acts like particles. What? So here we go. All right. So this is a vacuum tube. What's a vacuum tube? It's a tube that has nothing inside. Well, no air. All right, that's what we mean by vacuum. So there's no air inside this. It's completely evacuated, okay? All right, so here we go. So this is a piece of metal, and it's hot, and it's charged negatively. This is a piece of metal, and it's charged positively. This is a battery. We have a current. Remember, positive charge carriers, right? All right, so what we're going to do, okay, let's see. Hold on. Okay, so what we're going to do, we're going to heat this thing up. And when you get it hot enough, these electrons are going to be expelled, or whatever you want to call it. Right? The electrons are going to have so much energy they're not going to be bound anymore to the metal. And this is positive, so these electrons, where are they going to go? They're going to go here, right? Okay. All right, so let's go through this in gory detail. Okay, so number one, at normal temperatures, the electrons in this metal, they're bound, right? They don't leave the metal. They stay in the metal, right? Okay, so at normal everyday temperatures, the electrons in the metal are bound. All right, that's cool. Now, however, if you give these electrons enough energy, they will escape. I mean, why are they held to the metal? Well, because, there's electrical forces, right? And so, however, if you get these electrons energetic enough, they'll have enough energy to break through those bonds, and they'll be able to escape and, accelerate towards that positive anode, all right? So here's the thing. We're going to talk about this a lot. E0 is called the work function. Too bad they didn't call it W0, but whatever, E0, work function, is the minimum energy that the electron has to have in order to escape that metal, okay? So all right, that's it, okay? So if the electron has E0 or more than E0, it's going to escape the metal and accelerate towards the positive anode. All right, so this is called an electroscope. You may have seen it a long time ago in high school or elementary school or who knows what. It's a nice demonstration you see a lot of times in science classes. So this is a glass container. This is metal. This is metal. This is metal. So these are like aluminum foil or something like that. And typically, okay, if this is uncharged, so the metal foil is just like this, right? However, if you charge this thing, let's say negatively, you charge it negatively. Well, the negatives, they don't like each other, right? They repel each other. So they spread down here, and then they spread on the foils. So if all of the foils are negative, they repel, right? So it goes like that. Okay, so there you go, all right? So that's called an electroscope. Same thing, right? Just, you charge this, these foils, they repel, so they move away from each other. Not a big deal, all right? Now, so again, this just happens, when you charge it. However you want to, just charge it, and then, Okay, so this is the photoelectric effect. So here you have this electroscope, which is charged, and it's charged because the foils are spreading apart, right? Repelling each other. So what you do, you take some ultraviolet light, and I'll explain later why it has to be ultraviolet, and you shine it on this. And look what happens. For some reason, which we'll discuss, the electrons are ejected. And you know they're ejected because what happens here? You know, these foils used to be full of electrons, but now the electrons are gone, so they no longer repel each other. And by the way, it says here photoelectrons. They just call them photoelectrons because they're talking about the photoelectric effect. These are just, you know, regular, ordinary electrons, all right? So if you don't have to call them photoelectrons, just call them electrons. So what I'm really saying is that somehow the light causes the electrons to be ejected. And this has nothing to do with heat, remember? I mean, look at this. Here, you know, here we said we have a hot cathode, right? So we get this thing hot enough so these electrons are ejected. Well, here, you know, this has nothing to do with temperature. We're just shining light on it. And somehow the light is able to somehow transfer energy or something. We'll talk about it. So those electrons are ejected, okay? All right. So this is actually, this is like the principle of what's going on, right? Now this is a diagram of one of the earliest photoelectron effect experiments. So it's kind of like what we said before, right? You know, you have this metal, all right? But here, you know, before, remember, we were heating this thing up somehow. But now we're not heating it up, we're just shooting light at it. Okay, so let's read this whole thing. Oh, gosh. All right, so light hits this cathode, the electrons are ejected. So what do you call that? When you have electrons moving as a unit, that's a current, right? So this is a good review of electricity. So the photoelectrons, let's just say the electrons, form a current between the cathode and the anode. Yep, that makes sense. Okay, here's a battery or a voltage power supply, you know. The potential difference can be changed or reversed. You can do whatever you want to do with it. We will later on. The current can be measured, right, with an ammeter, remember that? While the potential difference, the light frequency, and the light intensity are varied. So that's what we're going to do, right? We're going to vary all sorts of things and see what happens. So that's what it is. All right, so let's talk about the experimental results. All right, number one, increasing the light intensity increases the current. Okay, so you see that here's the current, here's the voltage, and this is weak or dim light, this is intense light. So a more intense light causes a larger current. Well, that kind of makes sense, right? I mean, you know, what's intensity of light? Just means how many photons per second. You know, a bright light has a lot of photons per second. A dim light has a small number of photons per second. So, you know, if you have a lot of photons hitting this cathode, you're going to get a lot of electrons ejected, so you're going to get a larger current. If you have a super dim light, well, that means you don't have very many photons, so you're not going to kick out as many electrons, so you're going to have a small current. Okay, whoopee. All right, so that makes sense, right? You know, that makes perfectly good sense. So that agrees with, you know, that agrees with classical physics. There's not a problem there. Everything's good. All right, now comes the weird stuff. There's a threshold frequency of light that depends on the cathode material. What is that? Okay, this is what it is. So here's the current, which is, again, you know, how many electrons are, you know, being ejected, right? And this is the frequency of light. Remember? You know, here's our wonderful equation for waves. But with light, we have c. So the frequency can be anything as long as that times that equals the speed of light, right? Okay, so what this says is that I don't care how bright your light is, all right? I don't care. You're not going to get a single electron emitted unless the frequency of the light exceeds some threshold, okay? That's what it means, all right? No matter how intense the light, there's no current. There are no electrons emitted if the frequency of the light is less than some threshold, okay? All right. No matter how weak the light, no matter how weak the light, I don't care how dim it is, there is a current, there are electrons ejected if the frequency is greater than that threshold. Wow! Now that is completely contrary to classical physics. Classical physics just says, you just heat up this thing, and you get the electrons emitted. What in the world does frequency got to do with it? All right, so here we have it. Here we have something that completely disagrees with classical physics, which shows you that something is wrong with classical physics, right? Okay. Here's another experimental result. Regardless of the light intensity, the current appears instantly with no time delay. Now, classically, you're heating up this thing by some manner, and you're only going to get the electrons emitted after this thing is hot enough. And that takes a while. So classically, you expect a time delay. But when you do it when you do the experiment, what does it say? I don't care if you have bright light or dim light. The electrons are going to be emitted instantly. Now, that's weird. Okay. Completely, again, it disagrees with classical physics. So now we have two things to worry about, right? Oh, my goodness gracious. Okay, now we want to change. Now we want to change the experiment a little bit. Okay, so before we had this thing positive, right? So you have these electrons, you give them enough energy, and they see this positive piece of metal, and they're all excited, right? They get accelerated towards the positive. Okay, but now what we want to do is we want to switch the battery. So now we're going to make this thing positive. So the electrons want to stay there, right? We're going to make this thing negative, so the electrons don't want to go there. All right, so if delta V is made negative, like I just explained, the current decreases. Okay, right? I mean, because again, these electrons want to stay here. They don't want to go there, all right? And so if this is really, really small, you'll still get some electrons, right, that go from here to here. But if you keep cranking this thing up, making this more and more positive, making this more and more negative, well, the electrons are going to be less and less likely to travel this distance, right? It's kind of like throwing up a ball, If you can't throw a ball a mile high, right? Eventually, the ball's going to want to come back. Well, the electrons, if this is super, super, super negative, they're just not going to want to go there, right? They're going to be repelled from this negative, and they're going to be attracted to the positive. Okay, so if delta V is made negative as shown, the current decreases until at delta V equals minus V stop, the current reaches 0. The value of V stop is called the stopping potential. In other words, it's kind of like this. You throw up a ball, all right, as hard as you can. So let's just say, you can only, let's be crazy, right? Let's say you can throw it a half a mile up, right? So that's the maximum you can do. You just can't get any higher than that, Anything higher than that's always going to, you just can't do it, right? So here, if you get this thing, if you get this thing negative enough and this thing positive enough, you're not going to get any electrons to go here. They're all going to be stopped, right? None of them are going to reach that, okay? So what does it say? It says delta V equals minus V stop. Now, why do they say minus? Well, they just want V stop to be a positive number, okay? And so they put that minus in it just to emphasize that they switched it. But don't worry about that. All I'm saying is, so that's called the stopping potential, no current, all right? So V stop means no current. Now, so that's just a definition, all right? That's just a definition of V stop. Now, here's what's kind of interesting. Here's what's kind of interesting. So the value of V stop is the same for both weak light and bright light. A more intense light causes a larger current. Yeah, we knew that. But in both cases, the current stops when delta V equals minus V stop. Okay, we kind of just said that a minute ago, right? All right, so no current when this voltage, this is really very, very negative. This is very, very, very positive. So none of these electrons are going to hit this, okay? All right, we're going to use that in a minute. Don't worry. Let's see. All right, okay. So a more intense light causes a larger current. Yeah, we already said that. No current flows if delta V is less than minus V stop. Yeah, right? Right? So remember, V stop is a positive number, but negative, positive is negative. So this is voltage here, right? So this is some negative thing. The current is independent of delta V for delta V positive. Here's what's important. The stopping potential is the same for intense light and for weak light, right? Here's intense light, here's weak light. They both have the same V stop. What? Classical physics has nothing to say about that. So there's another problem, all right? That's another problem. Okay, now, and again, this is totally insane because, you know, like what we said earlier, in classical physics, if you have a super, super bright light, that's going to increase the temperature of the metal, right? And when the temperature of the metal is increased, that means that the kinetic energy of the electrons is increased. So you'd think that V stop would be increased. It's wrong, all right? Classical physics is wrong, you know? All right, so wrong. Oh, sorry. All right, so let's see. All right, so here's the experimental results. Let's just review them. Increasing the light intensity increases the current. Hey, that's a butt, sorry. Period. There's a threshold frequency of light that depends on the cathode material. Regardless of the light intensity, the current appears instantly, no delay. If delta V is made negative, the current decreases until at some particular value, minus V stop, the current reaches 0. The V stop is called V stop, stopping potential. The value of V stop is the same for both weak light and bright light. A more intense light causes a larger current, but in both cases the current ceases when delta V is minus V stop. Okay, I just repeated myself. All right, what's going on here, right? I mean, come on, what is going on here? People are totally confused. Well, guess who's going to rescue us? Einstein, okay? So Einstein to the rescue. So it's a half an hour, so let's quit.